Welcome back to Silicon to Software. I'm your host, Imran. Today we're talking about 6G, specifically why the hardware just isn't ready yet. Let's start with a picture. A surgeon in New York operating on a patient in Kenya through robotic hands with zero perceptible lag. That's the 6G promise. Autonomous cars talking to each other in microseconds. AI running right on the antenna outside your window. Sounds incredible, right? But here's the truth. Most coverage misses. The hardware for 6G isn't missing. Prototype transceivers exist. Lab links work today. The real problem is something else entirely. Can we build this stuff at scale, at a price that actually makes sense? With enough power efficiency to survive outside a lab? That's the real gap. And honestly, it's a much harder problem than most people realize. Quick note, before we go further, on that 100 times faster than 5G headline you keep hearing, it's marketing shorthand, not an official spec. Some 6G research is aiming for speeds around 50 times faster than 5G's official peak. Compared to real-world 5G speeds, sure, that multiplier climbs a lot higher, but there's no ratified number yet. Keep that one in your back pocket. So where's the actual holdup? 3 places: physics, heat, and manufacturing. First, physics. 6G wants to use the terahertz band, way higher frequency than 5G, which means more bandwidth, in theory. But terahertz signals are fragile. They lose strength fast. Water vapor absorbs them, walls block them almost completely. Regular silicon just can't handle these frequencies well, so engineers are turning to exotic materials. Gallium nitride, indium phosphide, gallium arsenide. These work in the lab, but they're expensive, hard to manufacture, and here's the catch: they don't fit into existing chip factories. And that's a massive problem. The entire global chip industry runs on silicon. TSMC, Samsung, Intel, all silicon. Switching materials isn't a small ask. Second, heat. Now here's what surprised me. Terahertz amplifiers actually run cooler than today's AI chips, so that's not the issue. The real issue is packing all that RF, digital, and power circuitry into tiny outdoor enclosures. Managing heat in that cramped a space is brutal engineering. The industry's answer right now is chiplet packaging, stacking different materials together on one substrate using techniques like CoWoS and Foveros. In 2026, 6G is just as much a packaging challenge as it is a materials challenge. And here's something specific to my world: PCB manufacturing. High-frequency laminates already exist. They're used in radar, aerospace, satellites. That part's mature. What's not mature is pushing those boards past 100 gigahertz. At those frequencies, copper roughness on the board itself starts killing your signal. The qualification standards weren't even written for this. Nobody in the mainstream press is covering this bottleneck. But it's real, and it's not solved. Now, antennas. This is where it gets genuinely interesting. 6G introduces something called reconfigurable intelligent surfaces. Think programmable walls that redirect signals around obstacles instead of just losing them. Genuinely cool technology. But it hasn't been standardized yet, and there's real debate in the industry about whether it actually goes mainstream or stays niche. Here's the bigger shift, though. It's not really about speed. 5G bolted AI on as an afterthought. 6G is being built AI native, from the ground up. AI baked into every layer of the network. That means base stations need to run continuous AI inference, not just push packets around. The chips for that exist separately today. The challenge is combining them, cramming powerful AI compute right next to sensitive radio hardware inside an outdoor box on a tight power budget. Nobody's cracked that exact combination yet at scale. There has been real progress, though. Researchers published a chip last year covering an enormous frequency range on a single piece of silicon, genuine milestone. but it still falls short of the frequencies 6G's biggest promises actually depend on. Now, security. This one gets almost no attention, and it should. AI running at the network edge massively expands the attack surface. And there's a looming deadline on top of that. Quantum computers will eventually break today's encryption. New quantum-resistant algorithms exist, but they're computationally heavy. Running them on power-starved edge hardware is just one more constraint stacked on an already brutal design problem. So, when does 6G actually show up? Most roadmaps point to the early 2030s, and even then, expect a limited rollout first. Specific corridors, campuses, industrial zones. Full blanket coverage takes years after that. Here's why. Software updates overnight. Spectrum gets allocated with a signature. But chips, substrates, antennas, thermal systems, those have to be designed, tested, manufactured, and physically installed. That timeline just doesn't compress, no matter how much hype builds around it. Bottom line, the physics works. The math works. What's missing is the hardware to deliver it at commercial scale, and that's exactly why this space is worth watching right now, not when the first 6G phone ships. That's it for today. For the full technical breakdown, sources, and the semiconductor comparison charts, head to silicontosoftware.com. Until next time.